Good morning, sir. My name is Shubham, and today's topic for our presentation is Booth's multiplication algorithm. And I'll be explaining the flowchart first, and later on we'll be moving on to solving the problem. So, in our presentation, this is the flowchart we are going to consider, and these are the naming conventions I've used, and the same naming conventions we are going to use in the problem and the flowchart as well. So, in this flowchart, we consider multiplicand and multiplier, two numbers for working on here, and there are a few assumptions we need to make at the start. There is AC, SC, and Qn plus 1. AC refers to accumulator, and Qn plus 1 is the extra variable we are going to use, and SC is sequence counter, where all of them are considered to be 0 at first at reset condition. And when we go ahead, we compare the least significant bit, which is Qn, and Qn plus 1, the extra bit we are going to use. And when we compare, they are just going to be side by side. There's no not going to be any operation. So after comparing, we see whether the number is 0 1 1 0, or both of them are same as 0 0 and 1 1. So in let's take first case as we find the number to be 0 1. So when we find the number to be 0 1, the first operation we are going to perform is AC plus BR, and we are going to store it in AC. So moving on, after the operation, we perform arithmetic shift, right, and also decrease the count of sequence counter by 1. And then we check whether our sequence counter value is 0 yet. So if it is 0, we are going to end the program, and if it is not 0, we are again going to repeat the step from comparing the two bits. So when we compare the two bits, and let's take for instance we have 1 0 as our comparison, and later on we perform the operation as AC plus BR, complement of BR plus 1. And later on when we go ahead, we also perform arithmetic shift right operation, and decrease the sequence counter by 1. And again we check whether the sequence counter is 0 yet. So if it is not, we repeat the steps, and if we get same numbers, we just perform arithmetic shift right, and we reduce the count of sequence counter by 1. So this is the flow chart of the Booth multiplication algorithm. We are going to take two numbers and multiply them now. So we have taken 7 and 3. 7 will be our multiplicand and 3 will be our multiplier, and we convert them into binary numbers. So we have 0 triple 1 for 7 and 0 0 1 1 for 3. And these are the few assumptions we are going to make at first, as mentioned in the flow chart. AC will be 0, SC will be SC will be 0 at first, and later on when we start solving the problem, it will be equal to number of bits we have. So number of bits here are 4 in both of the numbers. So going ahead, we also take Q1 plus 1 is as 0 in single bit, and when we start the problem, I have also written naming conventions here, you can refer to it. And we start the problem by naming down the columns. It's SC in the first column, AC as an accumulator, QR the multiplier, and Qn plus 1 the extra bit. And here we have BR as multiplicand, and the name of the operations we are doing. So at first, we write down the values of each and every name of the column, and the operation, there's no any such operation, so we are just naming it as initial values. So when we take SC as number of bits 4 and start with the problem, we compare the 0th bit of QR and Qn plus 1. So we have compared here the underlying numbers, and after comparing we come to know that it is 1 0, the comparison of two bits. And when it is 1 0, according to the flow chart, we are going to perform 2's complement addition. So using 2's complement addition, we get 110 as the answer. When we add AC plus complement of BR, which is this, plus 1. So after adding, we get the answer to be this. And Later on, rest of the bits are sorry. We get the answer to be this 1001, and the rest of the numbers are to be written as same, like their previous states. And later on, the next step of this next step of SC is equal to 4 will be arithmetic shift right. So when we shift right, our numbers are just going to shift right. We are not going to touch VR here. So when we shift right our numbers in arithmetic shift right, there's one condition where MSB is going to be the same. Sorry, MSB is going to be the same, and the number next to the MSB also is going to be the same. So we just have drawn the arrows here, which refers to same MSB and the next digit to the MSB. And after completing arithmetic shift right, we complete this step and reduce the counter sequence counter size by 1. So when we reduce the size, we check whether it is 0 yet. So it is not 0. So we take next step, which is SC counter. SC is equal to C, sorry. SC is equal to 3, and we compare the bits 1 and 0. So we have same bits here. According to the flowchart, when we have same bits, we do arithmetic shift right. And after doing arithmetic shift right, we just like we shift right and write VR as same, and again reduce the count of SC. So after reducing the count of SC, we see whether it is 0 yet. So it is not 0. And again we compare the bits. Sorry, we compare the bits which is 0 and 1. So for 0 and 1 we have addition in our flowchart. So after adding the two numbers, we get the answer as 0101. Adding AC and BR, we get answer 01 and 01, and rest of the bits are returned to be this return same. And later on, after every operation we perform, we always go through arithmetic shift right. So we also perform the same step, and later on we end the step and check whether the count is 1 yet. So it is 0 yet. So it is not 0, it is 1. So after performing arithmetic shift right, we again check the least significant bit of QR and Qn plus 1, and these are 0 again, which mean the same numbers. So after having same numbers, we perform arithmetic shift right operation, and after performing arithmetic shift right operation, we decrease the counter by 1. So after decreasing, we get the answer as 0. So we end the program. So after ending the program, we need to know how do we find the answer. How do we know that 7 into 3 is 21? So we get the AC and QR here and convert it into decimal numbers. So everyone knows how to convert binary to decimal. So after converting, we get the answer as 21. So this is Boole's multiplication algorithm. I'll just show the table of the problem, which may look better here. So this is the table we have. And moving on, we also know how to find the final answer. So here in conclusion, we also come to know that we don't have to use any extra steps. All we have to do is use addition and 2's complement addition, normal addition and 2's complement addition to perform the multiplication here. And this multiplication method is more efficient and can be performed faster than the regular multiplication in the processor. So we also conclude that it speeds up the process and also can be used in RTL design after parameterizing it. And later on, so we have if we have any questions, you can ask.
So my question is that what exactly you will achieve through boot multiplier?
Sir, through boot multiplier we'll be using like normal addition and 2's complement addition. We don't have to make
Subtraction using 2's complement.
Yes, subtraction using 2's complement addition.
Okay.
And we don't have to perform any regular addition like the calculators and all. This is going to be far efficient and easy process for the processor to understand. And if we just give 2 bits, this operation will be completed very soon. And we also can consider this design as it consider like it takes less area, less time, and it consumes less power.
Okay. So when you this is your digital design topic.
Yes, yes.
So whenever you will try to design the architecture of boot multiplier to have RTL design, what should be your goals? How will you start this?
Mm.
What exactly you will do?
So will for RTL design, sir, will be basically just getting using flowchart. Will be designing the ALU, and after designing the ALU, we'll consider all the parameters we have. We'll try using a maximum resource sharing, and the speed should be high, less area, and less power should be taken. So these are the few parameters we need to consider in RTL design because it is mainly focused on these 3 constraints.
Okay. Okay. Thank you, Shubham.
Yes, sir.